Close your eyes for a moment. Go back to the classroom. The one with the low ceilings and the scuffed linoleum floor. The one that smelled of chalk dust and pencil shavings, and the particular, almost sweet musk of old paper. Go back to the moment when someone, a teacher, a parent, a well-meaning relative, placed before you a diagram of the solar system, a picture in a book, or perhaps a poster pinned to a corkboard, the kind with curling edges and a faded sun that had been absorbing fluorescent light for years. You remember that image, don't you? Of course you do. Everyone does. It is one of those foundational pictures that lodge themselves into the architecture of the mind so early and so deeply that we never really question them. The sun, round and golden and central, radiating thick yellow lines. The planets, strung along their orbits like beads on a wire, each labeled in a neat script. Mercury, small and close. Venus, a little larger. Earth, third from the sun, blue and perfect and implying everything about who we are. Mars, then the gap, then the enormous bulk of Jupiter, then the ringed majesty of Saturn, and on outward, growing colder and stranger, until finally, at the edge of the diagram, a small cold dot named Pluto. Or perhaps it had already been reclassified by the time you encountered that particular book. That image is beautiful. That image is also a kind of lie, not a malicious lie, not a cynical one. It is the gentlest, most well-intentioned sort of deception, the lie of convenience, the simplification made necessary by the fact that a piece of paper is flat and two-dimensional, and reality, as it turns out, is neither of those things. That diagram handed you a model of the solar system that made it comprehensible, mappable, drawable, teachable, and in doing so it stripped away an entire dimension of truth. It took something wild and tilted and three-dimensional and wobbling with orbital inclinations and cosmic eccentricities, and it ironed it flat, the way you might iron a crumpled sheet until all its texture disappears. This film is about that crumpling. This film is about what was pressed out of the picture. We are going to unflatten the solar system tonight. We are going to take that beloved, laminated, color-coded diagram and lift one edge of it, and then another, and watch it rise and curve and tilt and dissolve into something so much more strange and beautiful and disorienting than anything that could ever be printed in a textbook for children. And in doing so, we are going to encounter a question that seems simple, but is in fact one of the most philosophically vertiginous questions a human mind can sit with. Which way is up? Let us begin with what we think we know. The solar system, in the model we were given, is flat. The planets orbit the sun in more or less the same plane, a thin disk of orderly celestial mechanics. This is true, in the rough and useful way that a map of your city is true. It captures something real, something functionally accurate enough to navigate by, something that will get you where you need to go most of the time. But a map of your city does not capture the hills, the valleys, the bridges arching over rivers, the subways threading beneath streets. A map is not the territory. The solar system has hills. The solar system has valleys. And when we begin to look at those hills and valleys, when we begin to ask not just where the planets are, but how high above or below some imagined baseline they travel, when we begin to ask about inclinations and eccentricities, and the curious wobbles built into every orbit we know, something extraordinary starts to happen. The solar system stops being a flat diagram and starts being a three-dimensional sculpture, an object of astonishing asymmetric complexity, embedded in a galaxy that is itself tilted relative to everything we once thought was level. The word ecliptic is one of those technical astronomical terms that most people have heard but few people have truly absorbed. It comes from the Greek word for eclipse, which makes sense. Eclipses happen when the moon crosses the plane of the ecliptic, that imaginary flat circle traced by the Earth as it orbits the sun. In modern usage, the ecliptic plane is essentially the reference plane for the solar system. It is, by convention, the zero line, the floor, the baseline from which we measure everything else. When astronomers say that Mercury's orbit is inclined at 7 degrees, they mean it is tilted 7 degrees relative to the ecliptic. When they say Pluto's orbit is inclined at 17 degrees, they mean the plane of Pluto's orbit is 17 degrees above and below the plane of Earth's orbit. But here is the thing about the ecliptic that should give you a small productive vertigo. It is not a real thing. It is a convenience, a human agreement, a cartographic decision made by astronomers who needed a reference plane, who needed a zero, and chose the plane of Earth's own orbit because Earth is where we happen to live and observe from. If we were Jovian astronomers floating in the methane storms of Jupiter, We might choose Jupiter's orbital plane as our zero. If we were some inconceivably advanced civilization perched on a rogue planet tumbling through interstellar space, we might choose the plane of the Milky Way, or the plane of the local galactic sheet, or the plane defined by the cosmic microwave background, the faint, cold light that fills all of space equally and contains, buried in its slight temperature variations, the deepest geometry of the universe. There is no cosmic floor. There is no universal ceiling. Up and down, high and low, above and below. These are the most parochial of all spatial concepts, the most stubbornly local, the most completely and thoroughly earthbound ideas that the human mind has ever generated. We evolved in a gravitational well on the surface of a rocky planet, and that gravitational well defined a direction we called down, and everything else became up, and we spent thousands of years assuming these directions meant something beyond the surface of our particular small rock. They don't. They are the compass directions of our specific location, as meaningful in the cosmic context as the north end of a magnet is meaningful to an astronaut floating in freefall. But before we dissolve all directions entirely, before we follow this thread of unlearning all the way to its terrifying and beautiful terminus, let us first understand how the solar system came to have even the modest flatness it does have, because that flatness is real, and it is remarkable, and it is the product of one of the most elegant and inexorable principles in all of physics. Go back far enough, about 4.5 billion years, and there was no solar system here at all. There was a cloud, a vast, cold, slowly rotating nebula of hydrogen and helium, and trace quantities of heavier elements forged in the hearts of earlier stars that had lived and died before our sun was born. This cloud was enormous, stretching across light years of space, irregular in shape, stirred by the distant shock waves of ancient supernovae, threaded through with magnetic fields and cosmic rays and the accumulated debris of stellar generations long past. This cloud was rotating, very slowly, almost imperceptibly, but rotating nonetheless, perhaps disturbed by the gravitational gradient of a passing star cluster, perhaps given its initial spin by the asymmetric pressure of a nearby supernova, perhaps simply inheriting the net angular momentum of the larger gas cloud from which it was drawn. Whatever the origin of that initial rotation, it was there, a tiny, gentle bias toward one particular direction of turning. And then, we think, the exact trigger is still debated. Something caused this cloud to begin collapsing under its own gravity, perhaps a shockwave from a nearby stellar explosion, a ripple in the fabric of the interstellar medium that slightly compressed the cloud and tipped the delicate balance between the outward pressure of gas and the inward pull of self-gravity, letting gravity win. The cloud began to fall inward, and here is where the most important physical principle in this entire story enters the frame: the conservation of angular momentum. You know this principle, even if you don't know the name. You have seen it in action every time you watched a figure skater spin. When a skater draws her arms inward toward her body, she spins faster. When she extends them outward, she slows. No one is pushing or pulling her. No external force is being applied. What is happening is the conservation of something, angular momentum, which is essentially the product of how fast something is rotating and how far its mass is distributed from the axis of rotation. When the skater pulls her arms in, she reduces the distance of her mass from her axis, so the rotational speed must increase to keep the total angular momentum constant. This is not something that happens sometimes, or usually, or when convenient. It always happens. It is one of the most rigorously observed laws in the universe. Now apply this to the collapsing cloud. As the cloud falls inward, the radius of its rotation decreases. The mass that was distributed across light years begins to concentrate. And just as the skater's arms drawing inward causes her to spin faster, the collapsing cloud begins to spin faster and faster as it contracts. The gentle, almost imperceptible rotation that the cloud began with amplifies, and amplifies, and amplifies, until the inner regions of the collapsing cloud are rotating with enough velocity to resist further collapse in the plane of that rotation. But gravity continues to pull everything toward the center along the rotational axis, from above and below the spinning disk, because there is no centrifugal force acting in those directions. Material falls freely inward from the poles of the rotating cloud while being flung outward by rotation in the equatorial plane. The result is inevitable. The cloud flattens. It collapses vertically much more readily than it collapses horizontally, and the initially spherical cloud becomes first an oblate spheroid, then a flattened disk, then a thin protoplanetary disk spinning around the bright, hot, condensing blob at its center that will become our sun. This is how you make a solar system. You start with a sphere and spin it into a disk. The textbook diagram, for all its simplifications, has captured this fundamental truth. The solar system really is mostly flat. The planets really do orbit in more or less the same plane, because they formed from material that had all settled into the same rotating disk before it condensed into planets. This is not a coincidence or a cosmic accident. It is the direct and inevitable consequence of angular momentum conservation in a self-gravitating cloud of gas, and it would happen anywhere in the universe where similar conditions prevailed. Other solar systems around other stars are also mostly flat for the same reason. It is a universal law producing a universal structure. Spin plus gravity plus time equals sine disk. But mostly flat is not the same as flat, and it is in the difference between those two things that tonight's real journey begins. The protoplanetary disk that formed our solar system was not a geometric ideal. It was a physical object, real, turbulent, lumpy, affected by magnetic fields and radiation pressure and the gravitational interactions between its own condensing clumps of material. As planets formed within this disk, each one inherited the local inclination and eccentricity of the material from which it grew, which was itself slightly out of plane, slightly perturbed, slightly inclined. And after the planets formed, they continued to nudge and pull on one another through gravity, gradually exciting inclinations, pumping eccentricities, altering orbits through a process called gravitational stirring that continues to this day, 4.5 billion years after the disk first appeared. The result is that every planet in the solar system orbits in a plane that is at least slightly different from every other planet's orbital plane. And some differ from the baseline ecliptic by amounts that, were they drawn accurately in that childhood textbook, would have made the diagram look not like a tidy set of concentric rings, but like a handful of hula hoops thrown at a wall. We will come to the exact numbers soon. We will lay out the specific tilts and inclinations of each world one by one, building a picture so different from the textbook that by the time we finish, you may look at that familiar diagram with something like the fond exasperation one feels toward an old, beloved, thoroughly unreliable map. But first, a word about the subjective experience of unlearning, because this film is not only about orbital mechanics. It is about what happens to a mind when it is asked to give up a comfortable picture and replace it with a more accurate, but less immediately comprehensible one. The history of science is largely the history of this process. Comfortable pictures dissolving, replaced by stranger truths. The Earth at the center of the universe, comfortable, reasonable, intuitive. The Earth as a small planet orbiting an ordinary star, true and deeply disorienting. The Milky Way as the whole of existence, comfortable. The Milky Way as one of hundreds of billions of galaxies in a universe so large that the word large fails to encompass it. True, and almost impossible to hold in the mind without a certain vertigo. Tonight we are performing a smaller but equally real dissolution. Tonight we are unlearning flat. If this slow unraveling of familiar maps is resonating with you, if you find yourself wanting to dissolve more of what you think you know, consider subscribing to Sleep on Space and ringing the notification bell so you never miss a journey into the dark. We are a community of quiet explorers, and there is always room for one more. Let us begin at the center and work outward. Let us begin with Mercury. Mercury is the smallest planet in the solar system and the closest to the Sun, completing one orbit in just 88 Earth days, a year that is shorter than many of our seasons. It is a world of extremes. The side facing the Sun bakes at temperatures approaching 430 degrees Celsius, while the permanently shadowed poles harbor water ice in craters that have never seen sunlight. It is ancient and heavily cratered, a world that feels, when you study it carefully, like a relic, like a stone floor in a very old building, worn smooth in some places and buckled in others by the weight of geological time. And Mercury's orbit, that 88-day ellipse, is inclined to the ecliptic plane at 7 degrees. 7 degrees may not sound like much. In everyday terms, a 7-degree slope is gentle, a mild incline that you might not notice walking up it slowly. But apply that to an orbit, and you begin to appreciate its meaning. At maximum excursion from the ecliptic, Mercury rises about 0.45 astronomical units above or below the reference plane. An astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers. Mercury, at its greatest vertical displacement from the ecliptic, is nearly 67 million kilometers above or below the plane in which Earth orbits. That is roughly 70% of the distance from the Earth to the Sun, simply as a vertical offset, simply as a consequence of Mercury's orbital tilt. Look up at the Sun on any given day. Now imagine a point in space that is 70% of the distance between you and the Sun, but positioned directly above or below the plane of the solar system. That is how high Mercury can get above the ecliptic, and this is considered in planetary science a fairly modest inclination. Mercury is the most inclined of the 8 major planets, but even at 7 degrees, it is the tamest beginning to the tilted story we are about to tell. Why is Mercury inclined at all? The short answer is that the inner solar system was, in its earliest period, a violent and chaotic environment. The protoplanetary disk from which the inner planets formed was being stirred constantly by the gravitational interactions between forming planetesimals, the rocky bodies that were accreting into planets. Mercury, as the innermost planet, experienced particularly intense gravitational interactions, both from the young Sun and from the larger bodies forming farther out. Computer simulations of early solar system evolution suggest that Mercury's orbit has been gravitationally excited numerous times over its history, and that its current 7-degree inclination is actually a remnant of a much messier past that has been somewhat tamed, but only somewhat, by billions of years of gravitational settling. Venus, next outward, is more obedient, inclined only 3.4 degrees. Earth, whose orbital plane defines our zero line, is by definition at zero, though this is convention, not physical reality. Mars, the red planet, tilts at 1.85 degrees. The gas giants, Jupiter, Saturn, Uranus, Neptune, are all inclined by less than 2.5 degrees from the ecliptic. For the major planets, the solar system really is quite flat, really does conform relatively well to the picture in the textbook. And then you get to Pluto. Pluto was discovered in 1930 by Clyde Tombaugh, a young Kansas farmer's son who had taught himself astronomy and ground his own telescope mirrors before landing a position at the Lowell Observatory in Arizona, where he was assigned to systematically photograph the sky and look for a predicted 9th planet. He found it by comparing photographic plates, blinking back and forth between images of the same patch of sky, taken on different nights, and looking for any point of light that moved relative to the fixed background stars. In the blink comparator, on the morning of February 18, 1930, one small dot shifted. Pluto. For 76 years, Pluto was considered the 9th planet. Children drew it at the end of the textbook diagram, small and cold and lonely at the edge of the known solar system. It was demoted to dwarf planet status in 2006, a decision that still provokes passionate disagreement in certain circles. But regardless of how you feel about Pluto's taxonomic status, its physical characteristics are not in dispute, and those characteristics are fascinating. Pluto's orbit is inclined to the ecliptic at 17 degrees. 17 degrees, more than twice Mercury's already modest tilt. At its greatest vertical excursion from the ecliptic, Pluto rises or dips more than 13 astronomical units above or below the reference plane. 13 astronomical units is approximately 2 billion kilometers. For context, the average distance from the Earth to Saturn, a journey that has occupied NASA spacecraft for years, is about 9 astronomical units. Pluto, in its wanderings above and below the ecliptic, travels farther out of the solar system's midplane than the distance from the Sun to Saturn. And Pluto doesn't just tilt, it also follows a highly elliptical orbit that carries it from 29.7 astronomical units from the Sun at its closest point, or perihelion, to 49.3 astronomical units at its farthest point, or aphelion. This enormous eccentricity, combined with the steep inclination, means that Pluto traces a path through 3-dimensional space that looks almost nothing like the neat circular orbit assigned to it in the textbook. If you could somehow watch the solar system from a perspective outside it, watching Pluto orbit the Sun would look less like a planet following a circular track, and more like a ball thrown on a curved path that sweeps far above and far below the plane of everything else. But even Pluto's 17 degrees begins to seem almost conservative once we take a step further outward and encounter Eris. Eris was discovered in 2005 by a team led by astronomer Mike Brown at the California Institute of Technology. It is a dwarf planet in the scattered disk, the outermost and most dynamically disturbed region of the solar system, and its discovery was, Somewhat ironically, one of the primary reasons that Pluto lost its planetary status, because Eris was found to be slightly more massive than Pluto, and if Pluto was a planet, then so was Eris, and so were the growing number of Eris-like bodies being discovered in the outer solar system. Rather than expand the planetary club indefinitely, the International Astronomical Union decided in 2006 to create the category of dwarf planet and move both Pluto and Eris into it. Eris, this distant and disruptive world, orbits the Sun at an inclination of 44 degrees from the ecliptic. 44 degrees. Stop and feel the weight of that number. The ecliptic plane, the flat disk of the solar system as usually depicted, is sitting horizontally before you. Eris's orbital plane cuts through that disk at an angle steeper than 45 degrees. It is nearly perpendicular to the solar system's floor. If the solar system were a bowl, Eris's orbit would be cutting across it at an angle that would carry the bowl's contents up the side and nearly over the rim on both sides. In three-dimensional space, Eris's orbit carries it roughly 38 astronomical units above and below the ecliptic at its extremes. 38 astronomical units. That is farther from the ecliptic than the planet Neptune is from the Sun. Eris, in its vertical excursions, reaches heights above or below the solar system's midplane that exceed the entire span of the classical solar system. When astronomers calculate the orbital properties of Eris, what they find is a body that barely seems to belong to the same solar system as Venus or Mars or Jupiter. It is a world that has been gravitationally scattered to an extreme orbital configuration. The result, most models suggest, of close encounters with Neptune billions of years ago that kicked Eris into its current tilted, elongated, eccentric path. Eris is, in a sense, a refugee from the orderly solar system, a world that tried to exist in the flat disk and was violently ejected from it, flung into the third dimension like a stone thrown at an angle. To look at this diagram, the true three-dimensional diagram of the solar system's major bodies, for the first time, is to have a curious experience. The initial reaction is often something like disappointment. The elegant simplicity of the textbook picture is gone, replaced by something messier, harder to hold in the mind all at once. But that disappointment, if you sit with it, gives way quite quickly to something else, to a kind of intellectual pleasure that is the specific pleasure of seeing the reality behind the simplification, of graduating from the comfortable lie to the harder truth. The solar system is not a neat set of concentric rings. It is a collection of intersecting orbital planes, each one tilted at a slightly different angle, each one defining a slightly different version of flat. There is no single flat. There is no universal level. Every planet defines its own horizon. This should not surprise us when we think carefully about it. We know the planets formed from the same protoplanetary disk, so they share a rough commonality of orientation. Most of them are within a few degrees of the ecliptic. But rough commonality is not identity, and the perturbations of billions of years of gravitational interaction have nudged each orbit into its own distinctive configuration, like the separate plates of a clock that all share the same axis but each rotate at a different rate and angle. What we are looking at, when we look at the true three-dimensional solar system, is the history of gravitational dynamics written in the inclinations of orbits. Each tilt tells a story. Mercury's 7 degrees speaks to the violent churning of the inner solar system in its early period. Pluto's 17 degrees whispers of its complex dance with Neptune, of resonances and near misses played out over billions of years. Eris's 44 degrees shouts of a violent gravitational scattering event that threw this world out of the disk entirely and into its own steep orbital plane. A world that became a traveler between dimensions, crossing the ecliptic twice per orbit, and rising to heights that dwarf the classical solar system's scale. And we have not yet left the solar system. We have not yet ventured into the belt of rocky debris that girdles the solar system's middle reaches, where an asteroid with an orbital tilt so dramatic it seems almost impossible waits to illustrate just how extreme the departure from flat can become. We have not yet begun to talk about the vast spherical shell of icy bodies at the solar system's outer boundary, the structure that finally, definitively, fatally dissolves the notion of a flat solar system in the same way that running water dissolves sugar, completely and without remainder. And we have not yet looked up, or out, at the galaxy in which this entire wobbling, tilted, three-dimensional solar system is itself tilted and embedded. The larger context that makes the vertical dimension of the solar system look not like an anomaly, but like a symptom of a universe that has no interest whatsoever in being flat. But those are stories for the segments ahead. For now, sit with the numbers. 7 degrees, 17 degrees, 44 degrees. Hold them in your mind like weights on a scale. Let them tilt the scale. Let them tilt the picture you carry. The solar system is not flat. It never was. We are 20 minutes into a 2-hour journey to the edge of what up and down mean. If you find this kind of slow, thoughtful exploration of deep space genuinely nourishing, if it is the kind of thing you want more of in your life, consider subscribing to Sleep on Space and liking this video. Every subscription helps us continue making these long, quiet journeys into the dark. We are grateful for your company. There is a misconception about the asteroid belt that science fiction has worked very hard to install in the popular imagination, and it is the misconception of density. In the films, flying through the asteroid belt is a harrowing experience. Rocks everywhere, constant evasive maneuvers, the ship threading needles of stone at high velocity. The reality is almost its exact opposite. The asteroid belt is largely empty space. If you were to stand on any given asteroid in the belt and look around, you would almost certainly see no other asteroids. You might be able to identify the brightest ones as faint points of light against the background stars, if you knew exactly where to look. But for the most part, you would simply see the dark, star-sprinkled void that characterizes all of space. The main asteroid belt, which occupies the region between Mars and Jupiter, roughly 2.2 to 3.2 astronomical units from the Sun, contains millions of objects, but those objects are distributed across a volume of space so immense that their average separation is in the hundreds of thousands of kilometers. This is a useful corrective to the Hollywood picture. The asteroid belt is a place of great emptiness, dotted by occasional small rocky worlds. Worlds that are, in their own quiet way, as individual and as storied as any planet. Among those worlds, there is one that deserves particular attention for our purposes tonight. Pallas. Pallas is the second largest asteroid in the main belt, or at least one of the candidates for that title, depending on how you measure. It is a lumpy, roughly ellipsoidal body about 512 kilometers across at its widest, with a heavily cratered surface and an estimated mass that makes it one of the more substantial objects between Mars and Jupiter. It was discovered in 1802 by the German astronomer Heinrich Wilhelm Matthias Olbers, who was already famous for discovering the asteroid Ceres the previous year, and who would go on to have his own cosmological paradox named after him, Olbers' paradox, the question of why the night sky is dark if the universe is infinite and filled with stars. But Pallas's most remarkable property for our purposes is not its size or its age or its cratered surface. It is its orbital inclination. Pallas orbits the Sun at an inclination of 34.8 degrees to the ecliptic. 34.8 degrees. In the context of the asteroid belt, this is extraordinary. Most asteroids in the main belt orbit within a few degrees of the ecliptic, having settled into roughly the same plane as the planets from which they share origin material. Pallas, by contrast, cuts across the ecliptic at an angle so steep that it spends much of its time well above or well below the plane of the solar system, crossing through the ecliptic twice per orbit, and then soaring off into the vertical reaches of the solar system's middle region, like a bird that refuses to follow the flock. At its maximum vertical displacement from the ecliptic, Pallas rises or dips nearly 1.6 astronomical units above or below the reference plane. 1.6 astronomical units is farther from the ecliptic than Mars is from the Sun. The path of Pallas in three-dimensional space would, if traced as a glowing line, look less like an orbit in the familiar sense, and more like a steep, elongated loop that passes through the ecliptic plane briefly, before climbing high above it on one side and diving deep below it on the other. The reason for Pallas's extreme inclination is bound up in the same violent history that shaped the entire asteroid belt. The belt as we see it today is a remnant, a fraction of the material that was present in that region during the early solar system. Most of what should have been there was disrupted and expelled by the gravitational influence of Jupiter, whose enormous mass stirred the region so thoroughly that the material was prevented from ever accreting into a planet. What remained was the debris, asteroids ranging from tiny pebbles to bodies hundreds of kilometers across, scattered into a wide range of orbital configurations by Jupiter's gravitational stirring. Pallas appears to have survived in a particularly extreme orbital configuration, one that other asteroids might once have shared before being perturbed out of the belt entirely, or driven into the Sun, or ejected into the outer solar system. It exists in a sort of isolated pocket of orbital space, where its particular combination of inclination and distance from the Sun has proven stable over geological timescales, despite its dramatic departure from the ecliptic. When you think about Pallas, when you really try to visualize its path through space, something conceptually interesting begins to happen. We tend to think of the solar system as a flat place that has a few orbital eccentricities, a few objects that deviate from the rule. We think of the ecliptic as the real solar system, and these tilted objects as exceptions, outliers, anomalies. But as you accumulate the examples, Mercury at 7 degrees, Pluto at 17, Eris at 44, Pallas at 34.8, the exceptions start to feel less exceptional. You start to ask, what if the flat part is the anomaly? What if the 8 major planets, circling in their modest near-ecliptic orbits, are the minority report, and the true structure of the solar system is something far more three-dimensional, far more vertically extended than their tidy paths suggest? This suspicion deepens considerably when you leave the asteroid belt and venture into the Kuiper Belt, that vast disk of icy bodies beyond Neptune's orbit. The Kuiper Belt is the solar system's next major structural feature after the asteroid belt, and it has a character all its own, colder, darker, and in certain important respects, considerably puffier than the inner solar system's flat disk. The Kuiper Belt extends from roughly 30 to 50 astronomical units from the Sun, occupying a donut-shaped region of space that wraps around the outer solar system. It contains hundreds of thousands of objects larger than 100 kilometers in diameter, icy bodies rich in frozen water, methane and ammonia, and likely billions of smaller objects. Pluto is the most famous Kuiper Belt object. Eris, technically in the scattered disk region beyond the classical Kuiper Belt, is the largest known dwarf planet in this region. But the character of the Kuiper Belt differs from the asteroid belt in one particularly important way for our narrative. It is considerably more puffed up in the vertical direction, while the inner solar system's asteroid belt has most of its objects concentrated within a few degrees of the ecliptic. Kuiper Belt objects are distributed across a much wider range of inclinations. The classical Kuiper Belt has 2 dynamically distinct populations, a cold population with low inclinations of just a few degrees, and a hot population with inclinations ranging up to 30 degrees and beyond. And the scattered disk, the dynamically excited outer region where Eris resides, contains objects with inclinations spanning nearly the entire range from 0 to 90 degrees. What this means physically is that the outer solar system is not a thin disk. It is a thick, puffy, 3-dimensionally extended structure, less like a pizza and more like a slightly deflated ball, or perhaps like the thick lenticular shape of a lens, widest at the center, the ecliptic plane, but extending significantly above and below it. The Kuiper Belt is a 3-dimensional structure, and its vertical extent is one of its most interesting and least discussed properties. The vertical thickness of the Kuiper Belt, the range of distances above and below the ecliptic where significant numbers of Kuiper Belt objects are found, is roughly 15 to 20 astronomical units at its outer edges. 20 astronomical units, that is twice the distance from the Sun to Uranus, expressed not as a distance across the solar system but as a height above its midplane. The Kuiper Belt is, in its outer regions, nearly as tall as it is wide, more sphere than disk, more volume than surface. And the Kuiper Belt is just the beginning. Beyond the Kuiper Belt lies the scattered disk, where Eris and its kin orbit in inclined eccentric paths that carry them from the inner solar system to hundreds of astronomical units from the Sun. Beyond the scattered disk lies a region of space that is still poorly understood, but which may contain a significant population of bodies in even more extreme orbits. Bodies whose gravitational interactions with an as yet undetected large outer planet, sometimes called Planet 9 or Planet X, may be responsible for some of the orbital clustering observed in the most distant trans-Neptunian objects. And beyond all of this, beyond the scattered disk, beyond the hypothetical Planet 9, beyond the farthest reaches of what we might confidently call the planetary solar system, lies the structure that ultimately defeats flatness entirely, the Oort Cloud. We have not yet arrived there. We are building toward it, as one builds toward a climax in a piece of music, layer by layer, gathering momentum, allowing the ear to anticipate the arrival before it comes. Because the Oort Cloud is not simply the next structure in the solar system, It is the structure that dissolves the very concept of a solar system boundary, the structure that makes the flat disk of the ecliptic look like a thin line on a page, rather than a meaningful division of space. But before we arrive at the Oort Cloud, there is still more to say about the vertical dimension of the inner and middle solar system, about the ways in which orbital inclinations are not random but are instead patterns that tell stories about the history of our cosmic neighborhood, about the forces that shaped it and continue to shape it, about the deep geological time in which planets are moved and changed and scattered the way pebbles are moved and scattered by a river. Every inclination is a history, every tilt is a record. The solar system is not merely a spatial object, a collection of bodies distributed in three-dimensional space. It is a temporal object, a structure whose current configuration is the result of 4.5 billion years of gravitational dynamics, of close encounters and resonances and scattering events, of the accumulated decisions of physics played out over timescales that make human history look like a single heartbeat. When you know the inclination of an orbit, you know something about its past. You know that this body was once somewhere else, that something moved it, that the current configuration of the solar system was not inevitable but contingent, the result of a chain of physical events that could, in principle, have gone differently and produced a very different arrangement of the same bodies. Mercury might have been kicked to a higher inclination or expelled from the solar system entirely during the late heavy bombardment, 4 billion years ago. Pluto's 17-degree tilt is the signature of a complex gravitational dance with Neptune that played out over hundreds of millions of years. Eris's 44 degrees is the mark of a violent scattering event, whose details we are still working to reconstruct from the orbital evidence it left behind. Pallas's 34.8 degrees is a mystery that continues to challenge dynamicists, a steep tilt in the middle of the belt that seems to have persisted for billions of years despite the powerful stirring of Jupiter nearby. These inclinations are the solar system's autobiography. They are the dimension that the flat textbook diagram cannot show. 30 minutes into our journey, and we have barely begun to dissolve the flat. We are still within the planetary solar system, still within the bounds of what could in principle be drawn on a piece of paper, however imperfectly. In the next 30 minutes, we leave that behind entirely. If this journey is worth making, consider subscribing to Sleep on Space, and please like this video if it moves you. Your support keeps these long, quiet expeditions possible. Picture the following. You are standing in a vast, dark field at night. It is autumn, and the air is cold, and the sky is completely clear. The kind of sky that only exists far from city lights, where the Milky Way is a luminous band and not an abstraction. Before you, in the middle of the field, someone has placed a single coin, a small, thin disc, no larger than your thumbnail, lying flat on the ground. You walk toward it and lean down to look at it. It is perfectly flat, perfectly circular, perfectly thin in relation to its diameter. Now imagine that this coin is the ecliptic plane of the solar system, the flat disk in which all the major planets orbit, and now imagine that surrounding that coin, at a distance of roughly 2,000 times the coin's diameter, and extending in all directions, up, down, sideways, forward, backward, in every conceivable three-dimensional direction, there is a shell, a thin, invisible shell, but a shell of ice, billions of icy bodies, each separated from its neighbors by vast distances of empty space, but collectively forming a rough sphere, a bubble of frozen material wrapped around the solar system at an enormous radius. This is the Oort Cloud. The Oort Cloud is named for the Dutch astronomer Jan Hendrik Oort, who in 1950 proposed its existence to explain a mystery that had been puzzling astronomers for decades: the origin of long-period comets. Long-period comets are those with orbital periods greater than 200 years. Some have periods of thousands of years, some of tens of thousands, some so long that they have never been seen before by any human observer and may never be seen again. What is remarkable about these comets is the randomness of their orbital inclinations. Short-period comets, those with periods less than 200 years, tend to orbit in roughly the same plane as the planets, inclined only modestly to the ecliptic, consistent with an origin in the Kuiper Belt. But long-period comets arrive from all directions, at all inclinations. They come from above the ecliptic and below it, from the north pole of the solar system and from the south, from directions at right angles to the planet's orbital plane. Oort recognized what this meant. The reservoir from which long-period comets are drawn is not a flat disk like the Kuiper Belt. It is a sphere, a spherical shell of icy bodies wrapping the solar system in all directions, so that when something disturbs a body in this cloud, a passing star, a giant molecular cloud, the gravitational tide of the galaxy itself, that body can fall inward toward the sun from any direction, arriving as a comet on an orbit inclined at any angle to the ecliptic. The Oort Cloud is the solar system's spherical skin, and its dimensions are staggering. The inner edge of the Oort Cloud is thought to begin at roughly 2,000 astronomical units from the sun, about 300 billion kilometers. The outer edge is estimated to extend to 100,000 astronomical units or beyond, perhaps as far as 200,000 astronomical units in some models. Let us take a representative figure, the middle of this range, perhaps 50,000 astronomical units as the approximate outer boundary of the Oort Cloud. 50,000 astronomical units is approximately 0.8 light-years. A light-year, to refresh the intuition, it is the distance that light, traveling at 299,792 kilometers per second, the fastest speed anything in the universe can travel, covers in 1 year. 1 light-year is approximately 9.46 trillion kilometers. At the fastest speeds ever achieved by human spacecraft, the Voyager probes, traveling at about 17 kilometers per second, it would take approximately 17,000 years to travel 1 light-year. The Oort Cloud extends to approximately 0.8 light-years from the Sun. The nearest star to our Sun, Proxima Centauri, is approximately 4.24 light-years away. The Oort Cloud extends roughly 1/5 of the way to the nearest star, and this cloud, this vast, spherical shell of icy bodies, is not a disk. It is not even approximately a disk. It has no preferred plane. It has no ecliptic, no equator, no up or down in any useful sense. It is a sphere, surrounding the solar system in all directions, with equal thickness above and below the ecliptic, equal extension toward any arbitrary direction you might choose to call north or south, or up or down. When you include the Oort Cloud in your conception of the solar system, as you should, because it is gravitationally bound to the Sun and represents the outer boundary of the region where the Sun's gravity dominates over the combined gravitational pull of the rest of the galaxy. The solar system is not a flat disk at all. It is a sphere, an enormous sphere, with a radius of up to 0.8 light-years, surrounding the Sun in all directions. The flat part, the ecliptic plane where the planets orbit, is a thin kernel at the center of this sphere, a compressed disk whose total thickness, measured by the range of altitudes at which significant numbers of objects orbit, is perhaps a few tens of astronomical units, compared to the sphere's radius of 50,000 to 200,000 astronomical units. Think about that ratio. The flat part of the solar system is approximately 50 to 100 astronomical units thick, being generous. The spherical part is approximately 100,000 to 200,000 astronomical units in radius. The flat part, the part with all the planets and the beautiful rings of the textbook diagram, is roughly 1,000th the size of the full solar system, measured from the Sun's perspective. The vast, overwhelming majority of the solar system by volume is not flat. It is a sphere, and if you are a long-period comet being perturbed from the Oort Cloud and falling toward the Sun on an inward journey that will take thousands of years, you are traveling through a solar system that has no ecliptic, no flat reference plane that means anything to you. You are simply falling from a great spherical distance toward a bright point. And when you arrive in the inner solar system after your long journey, the ecliptic plane is just one particular slice through the space you have been traveling, a slice defined by the 8 planets that happen to orbit near it, no more fundamental than any other arbitrary plane through the center of the solar system. The ecliptic exists because we are here to name it. If the only inhabitants of our solar system were long-period comets, there would be no ecliptic. There would only be a sphere, and a central star, and the fall. The Oort Cloud also does something philosophically interesting to the question of the solar system's boundary. Where does the solar system end? This seems like a question with a clear answer. The solar system ends where the Sun's gravity gives way to the gravitational influence of other stars, where objects become more bound to the galactic field than to the Sun. But the Oort Cloud's outer edge is precisely in this transition zone, at 100,000 to 200,000 astronomical units from the Sun. The gravitational influence of the Sun and the combined gravitational pull of the galaxy are roughly comparable, and the objects in the outer Oort Cloud are perturbed by galactic tides and passing stars as much as they are by the sun's direct pull. This means the solar system does not end sharply. It dissolves. It fades gradually from something that is clearly part of the sun's family into something that is increasingly part of the broader galactic landscape. The outer Oort Cloud is a liminal space, a transition zone between solar and galactic, between local and cosmic, between the particular gravity of our particular star and the general gravitational background of the spiral arm of the Milky Way in which we are embedded. There is no clean line at the edge of the solar system, any more than there is a clean line at the edge of an atmosphere. The air just gets thinner and thinner until the concept of atmosphere dissolves into space. The solar system gets more and more diffuse, more and more susceptible to non-solar gravitational influences, until the concept of solar system dissolves into interstellar medium. This is the death of the boundary, and with the death of the boundary comes the death of the plane. If the solar system has no edge, if it fades into the galaxy rather than stopping cleanly, then the ecliptic plane, which is defined by the angular momentum of the inner solar system, by the specific geometry of that original protoplanetary disk, becomes less and less relevant as you move outward. At the orbit of Earth, the ecliptic is a powerful organizing principle. Nearly all the mass in the inner solar system lies within a few degrees of it. At the orbit of Neptune, it is still somewhat meaningful. Most Kuiper Belt objects are within a modest inclination of it. At the outer Oort Cloud, it means almost nothing. The distribution of objects is spherical, and the ecliptic is simply the name for one particular plane you could draw through the sphere's center, no more physically meaningful than any of the infinitely many other planes you could draw through the same point. The solar system, read from the outside in, is a progressive condensation from sphere to disk, a gradual gain of flatness as you approach the center, a gradual loss of three-dimensionality as the planet's orderly orbits replace the Oort Cloud's omnidirectional scatter. The textbook picture captures the very center of this structure, the most flat part, the most organized part, the most orderly part, and presents it as the whole, as if someone photographed only the eye of a hurricane and told you that was what a hurricane looked like. Before we leave the Oort Cloud and venture into the galactic context, before we take the even larger step that will place the solar system, flat disk and spherical envelope and all, into its relationship with the Milky Way, let us spend a moment with the concept of distance that the Oort Cloud forces upon us. The fastest human-made objects currently in interstellar space are the Voyager probes, launched in 1977 and now traveling at approximately 17 kilometers per second. Voyager 1, the more distant of the two, crossed the heliopause, the boundary of the solar wind, often cited as a candidate for the solar system's edge, in 2012 at a distance of about 121 astronomical units. It is currently the farthest human-made object from Earth. At Voyager's speed, reaching the inner edge of the Oort Cloud at 2,000 astronomical units would take approximately 300 years. Reaching the middle of the Oort Cloud at 50,000 astronomical units would take approximately 7,500 years. Reaching the outer edge at 200,000 astronomical units would take approximately 30,000 years. Roughly the time since the last Neanderthals walked the Earth. We have sent exactly one object beyond the heliopause, Voyager 1, and it is at 0.003 light-years from the Sun. The Oort Cloud begins at 0.03 light-years and extends to 0.8 light-years. We have not yet reached the Oort Cloud by any human technology, and at current speeds, our grandchildren's grandchildren's grandchildren will be the first humans living during a time when our fastest probes might be reaching its inner boundary. The Oort Cloud is not a theoretical construct for whose existence we have only indirect evidence. It is an inference, supported by the behavior of comets and the physics of solar system dynamics, but essentially unobservable directly with current technology. We cannot see individual Oort Cloud objects. They are too far away, too dark, too cold, too small. We infer the cloud from the statistical properties of the comets that fall inward from it, from the direction and distribution of their arrival trajectories, from the orbital periods that speak of distant origins. In a sense, the Oort Cloud is the solar system's dark matter, present, influential, inferred, but invisible. We know it is there because of what it does, not because of what we can see. This is one of the humbling facts of living in this solar system. The majority of it, by volume, is invisible to us. The Oort Cloud is by far the largest structure in the solar system, and we have never directly observed a single one of its constituent objects. What we call the solar system in our maps and our textbooks is really just the innermost fraction of a percent of the true solar system. The small, bright, warm kernel surrounded by the vast, dark, cold envelope that constitutes most of what gravitationally belongs to our sun. The solar system is mostly darkness. The solar system is mostly cold. The solar system is mostly vertical. We have just watched flatness die. Watched the orderly disk of the ecliptic dissolve into the enormous sphere of the Oort Cloud. The solar system revealing itself as a three-dimensional structure of almost incomprehensible scale. If this kind of deep space meditation is something you want to continue exploring, please subscribe to Sleep on Space. And if this video has given you a new way of seeing the sky above your head, consider sharing it with someone who might feel the same. We have been dissolving the flatness of the solar system from the inside, starting with the planets, moving outward through the Asteroid belt and the Kuiper Belt, arriving at the spherical Oort Cloud. Now we take the decisive step outside the solar system entirely and ask, how does this tilted, three-dimensional structure we have been examining fit into the larger context of the Milky Way? The answer begins to dissolve not just the flatness of the solar system, but the very notion that any particular direction is preferred. Any particular plane is fundamental. The Milky Way is a barred spiral galaxy, a rotating disk of approximately 200 to 400 billion stars, organized into a central bar structure with spiral arms extending outward from the bar's ends. The disk is roughly 100,000 light-years across, and roughly 1,000 light-years thick in the region where our sun lives. Our solar system is located in the Orion Arm, one of the Milky Way's minor spiral arms, approximately 26,000 light-years from the galactic center, roughly halfway between the center and the outer edge of the disk. The Milky Way has its own flat plane, the galactic plane, defined by the disk's rotation, just as the solar system has its ecliptic plane defined by the planet's orbits. And the relationship between these two planes, the ecliptic and the galactic, is one of the most underappreciated facts in popular astronomy. The ecliptic plane is tilted relative to the galactic plane by approximately 60 degrees. Let that number land. The flat plane in which Earth orbits the Sun, the reference plane for the entire inner solar system, the basis for all those inclination measurements we have been discussing, is itself tilted at 60 degrees to the plane of our galaxy. The solar system's floor is not aligned with the galaxy's floor. It is not even close to aligned. The solar system is, from the galaxy's perspective, cocked at a steep angle, its axis of rotation pointing not toward the galactic poles, but at an oblique direction, 60 degrees away from perpendicular to the galactic disk. This means that the solar system is cutting through the galaxy at a steep angle. Earth's orbit, which defines the ecliptic, is essentially running diagonally across the galactic plane, not parallel to it, not perpendicular to it, but at a 60-degree angle, which is as far from flat as you can get while still being measurably closer to flat than perpendicular. This 60-degree tilt has an immediately observable consequence that anyone who has ever looked at the night sky can verify, though most people have never thought about it in these terms. The ecliptic and the Milky Way are not the same thing. Look up on a clear, dark night, and you will see the Milky Way as a luminous band arching across the sky, the combined light of hundreds of billions of stars viewed from our position within the disk. And you will see the ecliptic as a different band, the zone of the zodiac constellations, the path along which the sun, moon, and planets appear to move. These two bands are not the same band. They cross each other at approximately 60 degrees, just as the planes they represent are tilted 60 degrees to each other. In June and December, when you look toward the points where the ecliptic and the Milky Way intersect, you are looking along the line where the solar system's flat plane meets the galaxy's flat plane. The fact that the solar system is tilted 60 degrees to the galaxy is not a well-known fact in the way that, say, the distance from the Earth to the Moon is well known. It does not appear in most popular astronomy books. It is rarely mentioned in documentaries. It is absent from the textbook diagrams. And yet it is one of the most significant single pieces of information you can have about the solar system's place in the cosmos, because it tells you something fundamental about the relationship between the local and the cosmic, between the particular orientation of our small system and the general orientation of the larger structure in which it is embedded. The solar system did not form in the galactic plane. It formed in a molecular cloud that was itself inclined to the galactic plane, a cloud that had its own angular momentum, its own rotation axis, its own spin, which was not aligned with the galaxy's spin, and so the solar system, inheriting its orientation from that molecular cloud, spins at 60 degrees to the galactic disk. The Sun and all its planets are, from the galaxy's perspective, running slightly diagonally, not quite with the flow of the galactic traffic, but cutting across it at an oblique angle. This is not unusual for a star in the Milky Way. In fact, the wide range of orbital inclinations relative to the galactic plane is a characteristic feature of the Milky Way's stellar population, and understanding that range is crucial to understanding the structure of the galaxy itself. Stars in the galactic disk have a range of orbital inclinations to the galaxy's midplane, just as asteroids in the asteroid belt have a range of inclinations to the ecliptic. The ones with low inclinations close to the galactic plane are considered to belong to the thin disk population. Those with higher inclinations, which swing farther above and below the galactic plane, belong to the thick disk population. And the stars with the highest inclinations, essentially orbiting the galactic center at large angles to the disk, belong to the halo population, the ancient, metal-poor stars that formed in the galaxy's earliest period and which still trace their highly inclined paths billions of years later. Our Sun is a thin disk star. Its orbit around the galaxy is relatively close to the galactic plane, with an inclination that carries it only a modest distance above or below the galactic midplane. But a modest distance, in galactic terms, is still a significant vertical excursion. The Sun does not orbit the galactic center in a perfect circle lying flat in the galactic plane. It traces an orbit that oscillates above and below the galactic midplane, with a period of approximately 64 to 70 million years. As the solar system moves around the galaxy, a journey that takes approximately 225 to 250 million years, a period known as a galactic year or cosmic year, it slowly bobs up and down through the galactic plane like a horse on a cosmic carousel. The amplitude of this bobbing is roughly 230 light-years above and below the galactic midplane. Not 230 astronomical units, 230 light-years. Given that 1 light-year is approximately 63,000 astronomical units, the Sun's vertical oscillation takes it to a height above the galactic plane that is approximately 14 million times the distance from the Earth to the Sun. We are currently, as best as can be determined from measurements of the local stellar density, approximately 56 to 93 light-years above the galactic midplane, slightly to the north if we define north as the direction away from which the south pole of the galaxy faces. We are in the upswing of our current cycle, moving away from the galactic plane at roughly 7 kilometers per second, and we will reach our maximum displacement of about 230 light-years above the galactic plane in approximately 30 million years before gravity from the dense galactic disk begins to pull us back toward the midplane. Think about this in terms of the historical timeline. The last time the solar system was at its current distance above the galactic plane on this particular cycle was roughly 64 to 70 million years ago, approximately the time of the Cretaceous-Paleogene extinction event that ended the dinosaurs. The time before that, when the solar system was last at this same point in its oscillation, was roughly 130 to 140 million years ago, in the Jurassic, when the large theropod dinosaurs were reaching their greatest diversity and size. The time before that, another oscillation period back, was roughly 200 million years ago, near the end of the Triassic, close to the Triassic-Jurassic extinction event. The correlation between these major geological and biological events and the solar system's passage through or near the galactic midplane has been noticed by many researchers, though the causal mechanism, if any, is still debated. One hypothesis is that when the solar system passes through the galactic midplane, it passes through the densest region of the galaxy's material, including giant molecular clouds, and encounters a higher density of gravitational perturbations that disrupt the Oort Cloud, sending showers of comets into the inner solar system and increasing the rate of large impacts on Earth. This is speculative, and the correlation may be coincidental, but it is an intriguing example of how the solar system's vertical position in the galaxy, how high or low it sits above the galactic plane, might have direct consequences for the history of life on Earth. The vertical dimension of the solar system, in this context, is not just an astronomical abstraction. It may be a biological variable. The height of the solar system above the galactic floor may be one of the factors that has shaped the history of life on our planet, tilting the probability of extinction events, modulating the flux of energetic particles and gravitational perturbations that the Earth has experienced over geological time. Up and down, in the galactic context, may be matters of life and death. There is something mesmerizing about this image. The solar system as a tiny bobbing point on a cosmic carousel, circling the galactic center while oscillating gently up and down through the plane of the galaxy. It is perhaps the most accurate single image of our cosmic position that can be conveyed in human terms. We are not sitting still in space. We are not circling serenely in a fixed orbit. We are bobbing and drifting and tilting, moving through the galaxy in a complex three-dimensional trajectory that no simple diagram could fully capture. And the galaxy itself is moving. The Milky Way is not standing still in the universe. It is moving toward the Andromeda galaxy and the larger structures of the cosmic web at hundreds of kilometers per second. It is falling, along with dozens of other galaxies in the local group, toward the Virgo cluster at about 300 kilometers per second. It is caught up in the large-scale flow of matter toward the Great Attractor, a massive concentration of mass hundreds of millions of light-years away. At approximately 600 kilometers per second, everything is moving, everything is tilted, everything is in a relationship of inclination with everything else. The flat textbook diagram was not merely a simplification. It was a frozen frame in a cosmic film that has been playing for 13.8 billion years and shows no sign of stopping. Every orbit is a trajectory through time as well as space. Every inclination is a record of forces applied and deflections sustained over geological and astronomical timescales. The solar system's 60-degree tilt relative to the galaxy is not a static fact but a dynamic situation, a relationship between angular momenta, each one pointing in its own direction, each one a consequence of the particular history of the object that possesses it. When you look up at the Milky Way on a clear night, you are looking not just at a collection of stars, but at a plane, the galactic plane, the organizing principle of the galaxy, the equivalent of the solar system's ecliptic but at a vastly larger scale. And the fact that you have to look up at an angle to see it, that the Milky Way cuts across the sky at roughly 60 degrees to the apparent path of the sun, is a direct visible consequence of the solar system's tilt relative to the galaxy. The sky itself is a diagram of inclination. We are halfway through our journey, having traveled from the first wobble of Mercury's orbit to the vast oscillation of the solar system through the galactic plane. If this journey is one you want to continue, please subscribe to Sleep on Space and leave a like. We make these films for the people who want to sit with the vastness of space and feel it slowly dissolve the ordinary. Thank you for being here. We have been accumulating a problem. We have been talking about up and down, above and below, high inclination and low inclination, as if these terms have straightforward meaning. And in the practical context of solar system astronomy, measuring orbital inclinations relative to the ecliptic, comparing the tilt of one orbit to another, they do have meaning. The ecliptic gives us a reference, and relative to that reference, inclinations can be measured and compared and expressed as numbers that are genuinely informative about the structure of the solar system. But the ecliptic is a choice. It is a convention. It is a zero line defined by the orbit of one particular planet around one particular star, chosen because that planet is where we happen to live and do our astronomy. And the question we need to sit with now, the question that the galactic context forces upon us, is, what does up mean when there is no privileged reference plane? In everyday life, up and down are defined by gravity. The direction gravity pulls toward the center of the Earth is down. The opposite direction is up. This definition is perfectly clear, perfectly consistent, and perfectly meaningful for any object near the surface of a gravitational body. The center of gravity defines a down, and everything else is organized relative to that down. But in space, away from the surface of any gravitational body, this definition becomes ambiguous. In low Earth orbit, an astronaut feels weightless, not because gravity has disappeared. Gravity at the orbital altitude of the International Space Station is roughly 90% of its surface value, but because the astronaut and the space station are in free fall together, accelerating toward Earth at the same rate, which cancels out the apparent experience of gravity. In this environment, there is no felt down. Every direction is equally not down. The astronaut can orient herself in any direction, and the physiological sensation of falling or being pressed against a surface is absent. At the solar system level, the situation is similar but more complex. The Sun's gravity defines a set of directions toward the Sun and away from the Sun. But these are directions in the plane of the solar system's orbital disk, not a vertical direction relative to the ecliptic. There is nothing that physically prefers the ecliptic's orientation over any other plane through the Sun. If the solar system had formed with a different initial rotation axis, if the molecular cloud that collapsed into the Sun had been spinning in a different direction, all the planets would orbit in a different ecliptic, equally legitimate, equally their own reference plane. There are, however, some candidates for physically meaningful reference planes at larger scales. The galactic plane is one. It is defined by the rotation of the Milky Way as a whole, which is itself a consequence of the angular momentum of the galaxy, which is ultimately traceable to the distribution of matter in the early universe and the gravitational interactions between protoclusters billions of years ago. The galactic plane is not arbitrary. It is the plane of symmetry of the galaxy's mass distribution, the plane in which the density of stars and gas is highest. But the galactic plane is only meaningful for objects embedded in the Milky Way. At the scale of the local group of galaxies, the cluster of 50-odd galaxies that includes the Milky Way and Andromeda, the galactic plane is just another inclined plane, one of many possible reference planes in a three-dimensionally distributed collection of galaxies. The local group has its own plane of rough distribution, and the Milky Way is inclined to that plane at some angle, and the local group is itself tilted relative to the local supercluster, the Virgo supercluster, and the Virgo supercluster is embedded in an even larger structure, the Laniakea supercluster, which contains more than 100,000 galaxies and stretches across 500 million light-years of space. At each scale there is a reference plane, a disk of matter, a preferred direction defined by the rotation of the structure at that scale, and at each scale, the structure at the next scale up is tilted relative to it. Everything is tilted relative to everything else. Cosmologists have a tool that comes closest to providing an absolute reference frame, and it is one of the most extraordinary objects of discovery in the history of science. The cosmic microwave background. The cosmic microwave background, the CMB, is the faint thermal radiation that fills all of space with almost perfect uniformity, a remnant of the early universe when, approximately 380,000 years after the Big Bang, the universe cooled enough for neutral hydrogen to form and for photons to travel freely through space for the first time. Those photons have been traveling ever since, for 13.8 billion years, redshifting as the universe expanded, their energy diluting into the microwave part of the electromagnetic spectrum, arriving at us from every direction in the sky with almost exactly the same temperature, about 2.725 degrees above absolute zero. The CMB is the oldest light we can see. It is a snapshot of the universe when it was a tiny fraction of its current age and size. And it is isotropic, the same in all directions, to better than 1 part in 100,000. There are no preferred directions in the CMB. There is no axis about which it is symmetric, no equator along which it is brighter or hotter than elsewhere. It is, to a very high degree of precision, the most isotropic thing in the universe. The CMB provides the closest thing the universe has to an absolute reference frame. We can measure our velocity relative to the CMB, our proper motion, plus the motion of the Sun around the galaxy, plus the motion of the galaxy toward the Virgo cluster. And this is the most fundamental statement of how we are moving, that physics currently allows. The CMB frame is the frame in which the universe itself is, on average, at rest. But the CMB does not define a preferred direction. It defines a preferred frame, a preferred state of rest, but not a preferred axis. There is no CMB up or CMB down. The CMB is the same in all directions and therefore does not privilege any direction over any other. It is the final dissolution of directional preference, the proof that the universe, at its most fundamental accessible level, has no preference for any particular orientation. And yet, and here is the twist that makes this philosophically interesting, the CMB is not perfectly isotropic. It has tiny temperature variations at the level of about 1 part in 100,000, the seeds from which all the large-scale structure of the universe grew. The quantum fluctuations of the early universe, magnified by the inflationary expansion, imprinted in the photon distribution, and visible today as the slight temperature variations in the CMB map. And buried in these variations, cosmologists have found hints of structure, a slight preferred direction that some researchers have called the axis of evil, a pattern in the CMB temperature variations that seems to have a preferred orientation coincidentally aligned with the plane of the solar system. This observation, first noted in the WMAP satellite data and subsequently examined in the Planck satellite data, is either a profound cosmological discovery, suggesting a fundamental anisotropy in the universe at the largest observable scales, or it is a foreground effect, a contamination of the CMB signal by local emission from the solar system itself. The debate is ongoing and unresolved, but its implications, if the signal is real, are staggering. The largest observable structure in the universe might be organized in a plane that aligns, improbably, with the ecliptic of our small solar system. This would be extraordinarily strange, almost impossibly so. It would require some physical connection between the orientation of the solar system and the structure of the observable universe, perhaps through some quirk of the inflationary process that generated the initial fluctuations, perhaps through some subtle physical mechanism not yet understood. Most cosmologists believe this is a statistical artifact or a foreground effect. But the fact that the question can even be asked, the fact that the CMB's largest scale temperature patterns might or might not be aligned with the solar system's ecliptic, speaks to how deeply the question of preferred directions and privileged planes is embedded in modern cosmological inquiry. At the very bottom of the question of what up means, we find not a clean answer but a productive mystery. A universe that appears at its largest scales to be isotropic but which shows, at every smaller scale, a proliferation of preferred planes, each one locally meaningful and cosmically arbitrary, each one the consequence of some specific angular momentum acquired in some specific way at some specific time in the history of matter. Up is local, down is local, flat is local, the ecliptic is local, the galactic plane is local. Even the CMB frame, while the most fundamental reference available to physics, does not define a direction, only a state of rest. In the deepest sense, there is no up. There is only where you happen to be, and how fast you happen to be spinning. We are an hour into our journey, and we have just dissolved the concept of up at the cosmological scale. If this kind of slow dissolution of the familiar is the reason you are still awake, or the reason you are drifting gently towards sleep, we would be honored to have you subscribe to Sleep on Space and like this video. We make these films with care, and your support means we can keep making them. We have dissolved the flat. We have established the sphere. We have placed the solar system in its galactic context and watched it bob and tilt on the cosmic carousel. Now let us come back to the solar system with new eyes. Not the eyes of someone looking at a textbook diagram, but the eyes of someone who has begun to understand the full three-dimensional architecture of this extraordinary place. When you read the solar system in 3 dimensions, what you see is a structure organized at several different scales of flatness. A series of nested structures, each with their own degree of planarity, their own thickness to diameter ratio, their own relationship to the ecliptic reference plane. At the innermost scale, the terrestrial planets, Mercury, Venus, Earth, Mars. The solar system is extremely flat. The terrestrial planets all orbit within a few degrees of the ecliptic, and their orbital planes are all fairly close to one another. This is the flattest region of the solar system, the core of the original protoplanetary disk, the region where the sun's gravitational dominance and the dense packing of forming planetesimals kept everything close to the original disk plane. Even Mercury's 7-degree inclination, which seems dramatic compared to the other inner planets, is modest on the scale of what the outer solar system presents. Moving outward through the asteroid belt, the inclination distribution widens. While the majority of main belt asteroids orbit within about 10 degrees of the ecliptic, the tail of the inclination distribution extends much further. Bodies like Pallas at 34.8 degrees represent the high inclination population that survived the gravitational stirring of the early solar system. The asteroid belt as a whole is distinctly thicker than the inner planetary system. Its vertical extent is larger relative to its horizontal extent. At the Kuiper Belt, the structure thickens further. The classical Kuiper Belt's hot population extends to inclinations of 30 degrees and beyond. The scattered disk, where Eris resides at 44 degrees, has objects spanning nearly the full range of inclinations. The outer solar system, from the Kuiper Belt outward, is not a thin disk, but a thick, puffed-up structure that is noticeably three-dimensional even to the eye. And at the outermost scale, the Oort Cloud, all planarity is lost entirely, replaced by a sphere that is as tall as it is wide, that has no preferred equatorial plane in the way the inner solar system does. This nested architecture, from flat disk at the center to sphere at the periphery, is not accidental. It is the direct consequence of the physics of planet formation and the subsequent dynamics of the solar system over 4.5 billion years. The inner solar system is flat because it formed in a thin disk that has been preserved in its flatness by the gravitational dominance of the Sun and the relatively small number of gravitational perturbations acting on the inner planets. The asteroid belt is somewhat puffier because Jupiter's gravitational influence has been stirring the belt's inclination distribution for billions of years, gradually exciting the inclinations of asteroids out of the ecliptic plane. The Kuiper Belt is puffier still because it has been stirred more thoroughly by Neptune's gravitational influence, which scattered a large population of objects into highly inclined orbits billions of years ago. And the Oort Cloud is spherical because it exists at distances where the Sun's gravitational dominance is weakening, and galactic tidal forces, the gravitational gradient of the galaxy itself, can act in all directions with roughly equal efficiency, randomizing the orientations of Oort Cloud objects over billions of years. The galactic tidal force deserves a moment of explanation, because it is one of the key mechanisms responsible for both the sphericalization of the Oort Cloud and the delivery of long-period comets to the inner solar system. A tidal force is the difference in gravitational pull experienced across an extended object. The tidal force that causes ocean tides on Earth, for example, is the difference between the Moon's gravitational pull on the near side of the Earth and the far side of the Earth. The near side is pulled toward the Moon more strongly than the far side, creating a stretching effect. Similarly, the galactic tidal force on the solar system is the difference in the galaxy's gravitational pull across the solar system's extent. The side of the solar system facing the galactic center experiences a slightly stronger pull toward the center, and the side facing away experiences a slightly weaker pull. For the inner solar system, the galactic tidal force is completely negligible. The Sun's much stronger local gravity overwhelms it completely. But at the distances of the outer Oort Cloud, where the Sun's gravity has weakened to something like 1/10,000th of its strength at Earth's distance, the galactic tidal force becomes significant. It acts preferentially in the direction perpendicular to the galactic plane, pulling the Oort Cloud's north and south poles defined in galactic terms, slightly more strongly than it pulls the equatorial regions. This differential force is capable, over billions of years, of changing the inclinations of Oort Cloud orbits, of slowly randomizing them, of converting what might have been a more disk-like outer cloud into the spherical structure we believe exists today. The galactic tide also plays a crucial role in delivering comets from the Oort Cloud to the inner solar system. When a galactic tidal perturbation changes the orbit of an Oort Cloud body, it can reduce that body's perihelion distance, the closest point in its orbit to the Sun, enough that the body passes through the inner solar system and becomes visible as a long-period comet. The galactic tide is, in a sense, the mechanism by which the galaxy periodically dips its gravitational fingers into the solar system's outermost reservoir and flicks objects inward, sending icy visitors from the cold outer dark into the relative warmth of the inner solar system where we can observe them. Every long-period comet that has ever been observed, from the great comets of antiquity, blazing in the night sky and terrifying medieval populations, to the celebrated modern comets observed with sophisticated telescopes, every one of them is a visitor from the vertical dimension. They come not from the flat disk of the ecliptic, but from the spherical shell of the Oort Cloud, arriving at all inclinations, at all angles, to the plane of the solar system, bearing the chemical signatures of the earliest solar system, and delivering those signatures, sometimes, to the surface of planets. The most dramatic cometary impacts in Earth's history, events that may have delivered water and organic molecules to the early Earth, events that may have contributed to some of the great mass extinctions, were almost certainly long-period comets that arrived from the Oort Cloud, from the vertical dimension, at inclinations that carried them across the ecliptic from above or below. The vertical dimension of the solar system is not just an interesting geometric fact. It is a delivery mechanism. It is a source of comets, and comets are a source of material, water, organics, the chemical building blocks of life, that has profoundly shaped the history of Earth. There is a kind of poetry in this picture that is worth dwelling on. We live in the flat part of the solar system, the thin disk where the 8 major planets orbit in their comfortable near-ecliptic planes. where the sun's gravity keeps everything relatively organized, where the geometry of the protoplanetary disk has been preserved for 4.5 billion years. And we look up from this flat place at a vertical dimension that we barely perceive but which surrounds us on all sides, that contains more of the solar system by volume than we can see or directly interact with. Occasionally, perhaps once every few years, something comes down from that vertical dimension. A comet falls inward from the Oort Cloud, cutting across the ecliptic at a steep angle, briefly brightening in the night sky before swinging around the sun and heading back out into the outer dark. And we watch it, and we name it, and we study its orbit, and we use its orbital parameters, its inclination, its period, its perihelion distance, to reconstruct, forensically, the orbit it came from, and the perturbation that sent it inward. We are, in this practice, archaeologists of the vertical dimension. We are reading the fossil record of Oort Cloud physics in the observed trajectories of ancient ice. Every comet is a message from the spherical solar system to the flat one. Every comet is a reminder that the diagram in the textbook is not the whole story, that there is more to the solar system than can be printed on a flat page, more to our cosmic neighborhood than the 8 planets and their orderly orbits, more to the sky above our heads than the ecliptic and the familiar constellations of the zodiac. The vertical dimension is always there. Most of the time it is invisible. The Oort Cloud, dark and cold and distant, does not betray its presence in any way that ordinary observation can detect, but periodically it announces itself, sending a frozen emissary inward into the light of the inner solar system, a temporary visitor from the outer dark, reminding us that what we see is only a fragment of what is. 70 minutes in, and the comets are falling. If you are finding this meditation on depth and dimension valuable, please subscribe to Sleep on Space. It takes seconds, and it allows us to keep creating these long-form journeys into the dark. Leave a like if the comet's message resonates with you. We will be with you for the final 50 minutes of the journey. We have been speaking about the vertical dimension of the solar system primarily in terms of its present structure, the inclinations of current orbits, the current extent of the Kuiper Belt and Oort Cloud, the current tilt of the solar system relative to the galaxy. But the solar system has a history, and that history is as much a vertical story as a horizontal one. The evolution of inclinations over time, the vertical history of the solar system, is one of the most active and productive areas of current planetary science. It is also one of the most humbling, because what the models tell us is that the solar system we see today is not the solar system that formed 4.5 billion years ago. The planets have moved. The orbits have changed. What we observe now is the product of billions of years of gravitational dynamics, of near misses and resonances and migrations, of a history that was neither inevitable nor predictable from first principles. The story begins with the NICE model, named not for the French city, though that city does lend its name to the theory, but presented originally by a consortium of planetary scientists working in Nice, France in the mid-2000s. The NICE model proposed a revolutionary explanation for several puzzling features of the outer solar system: the particular orbital configuration of the giant planets, the existence of the Kuiper Belt in its current form, the occurrence of the late heavy bombardment, the period roughly 3.9 billion years ago when the inner solar system was subjected to an intense bombardment of large impactors, and the capture of the Trojan asteroids that share Jupiter's orbit. According to the NICE model, the giant planets, Jupiter, Saturn, Uranus, Neptune, did not always occupy their current orbits. When they first formed, roughly 4.5 billion years ago, they were much closer together and much closer to the Sun, embedded in a broad disk of planetesimals extending outward from just beyond their orbits. Over the first several 100 million years of the solar system's history, these planets gradually migrated, Jupiter moving slightly inward, the other 3 moving outward, driven by the exchange of energy and angular momentum with the planetesimal disk. Then, approximately 3.9 billion years ago, Jupiter and Saturn reached a 2:1 orbital resonance, a configuration in which Jupiter orbited the Sun exactly twice for every 1 orbit of Saturn. This resonance dramatically destabilized the orbits of Uranus and Neptune, causing them to be scattered to much larger orbits, while also destabilizing the entire outer planetesimal disk. Neptune, in particular, was thrown outward and migrated through the original Kuiper Belt region, scattering the vast majority of Kuiper Belt objects out of the solar system into the inner solar system as impactors, or into the highly inclined and eccentric orbits of the scattered disk. The few percent of Kuiper Belt objects that survived Neptune's migration are the classical Kuiper Belt objects we observe today, and the scattered disk population, including Eris, are those that were flung into highly inclined orbits by close encounters with Neptune during and after its migration. The vertical dimension was dramatically affected by this planetary reorganization. Before the NICE model's instability, the outer solar system probably had a much thinner Kuiper Belt, more disk-like, more confined to the ecliptic plane, and fewer highly inclined objects. The instability of the NICE model scattered objects into high inclination orbits, created the hot Kuiper Belt population, populated the scattered disk with highly inclined bodies like Eris, and sent vast numbers of objects into the Oort Cloud from what had been a more disk-like reservoir. In a very real sense, the present three-dimensional vertically extended structure of the outer solar system is a direct consequence of a dynamical catastrophe that occurred 3.9 billion years ago and lasted for tens of millions of years. The chaos of planetary migration is written in the inclinations of Kuiper Belt objects, in the tilted orbit of Eris, in the spherical structure of the Oort Cloud. These inclinations are not original. They were impressed upon the outer solar system during and after the giant planet reorganization. More recent work has extended the NICE model and proposed variations. Some suggest the instability occurred earlier. Some suggest there were originally 5 giant planets rather than 4, with the 5th being ejected from the solar system during the instability. Various models suggest different timings, different sequences of events, different degrees of chaos in the early solar system. The details are still being worked out, but the broad picture is consistent. The solar system has a violent youth, a period of several hundred million years in which the giant planets were not where they are now, in which the outer solar system was dramatically reorganized, in which billions of objects were scattered into highly inclined orbits or expelled from the solar system entirely. The three-dimensional structure of the solar system is, in large part, a fossil record of this violence. When we measure the inclination of a Kuiper Belt object, we are reading the signature of a gravitational interaction with Neptune that occurred billions of years ago, perhaps during the late heavy bombardment, perhaps during the initial migration. When we measure the inclination of Eris at 44 degrees, we are reading the signature of a particularly close encounter with Neptune that flung this body into an extreme orbit. When we infer the spherical structure of the Oort Cloud, we are reading the signature of billions of years of galactic tides and stellar perturbations, acting on a population of objects that was originally delivered to large distances by the giant planet migration. The vertical dimension is history. It is archaeology. It is the three-dimensional record of everything that happened to the solar system in all the time it has existed, and the solar system continues to evolve. It is not a static system. It is a dynamical system, still changing, still slowly stirring. Computer simulations of the long-term future evolution of the solar system reveal a disconcerting possibility. The inner solar system is not fully stable on billion-year timescales. The equations governing the motions of the planets are chaotic, meaning that tiny differences in initial conditions grow exponentially over time, making long-term prediction impossible beyond a few tens of millions of years. In the 1990s, planetary scientist Jacques Lascar showed that the orbit of Mercury is chaotically unstable on timescales of a few billion years, that there is a small but non-negligible probability, approximately 1 to 2%, that Mercury's orbital eccentricity could become so large in the next 5 billion years that Mercury could either be ejected from the solar system, collide with the Sun, or, in the most dramatic scenario, have a close encounter with Venus that destabilizes the inner solar system and leads to a collision between Earth and Mars. This is not a likely outcome. The 98 to 99% outcome is that the inner solar system will remain more or less as it is for the Sun's remaining lifespan, but the 1 to 2% probability of catastrophe is not zero, and the mere possibility speaks to the fact that the solar system's current configuration is not eternally stable. It is a current snapshot in a long dynamical evolution that could, in principle, undergo dramatic changes, and in this dynamical evolution, inclinations are key. The scenario in which Mercury causes inner solar system chaos involves first a dramatic increase in Mercury's orbital eccentricity and inclination, its orbit becoming more and more tilted and elongated until it intersects the orbits of Venus or Earth. The vertical dimension of the solar system is not decorative. It is a degree of freedom in which instability can grow, in which the chaos of long-term orbital dynamics can express itself. The solar system may be quieter now than it was in its youth, but it is not finished changing. The vertical dimension is not closed. We have been on this journey now for well over an hour, and I want to take a moment to acknowledge something about the experience of absorbing all of this. The numbers, the scales, the concepts, the history. It is a lot. The human mind was not built for astronomical scales. We evolved to navigate environments measured in meters and kilometers, to track timescales measured in days and years. The scales of astronomy, light years, billions of years, millions of astronomical units, do not map onto any intuitive faculty we possess. They must be held abstractly, symbolically, as numbers that we know but cannot truly feel. And yet, there is a kind of feeling that comes with sustained contemplation of these scales, even if it is not quite the immediate visceral feeling of climbing a mountain or crossing an ocean. It is a quieter feeling, something like the feeling of standing at the edge of a very large body of water and looking out at the horizon and knowing, intellectually, that the water extends much farther than you can see. You do not feel the full extent of the ocean. You cannot, but you feel something of it, a sense of scale beyond your immediate perception, a kind of respectful awe at the existence of something so much larger than yourself. That is the feeling this film is trying to cultivate. Not the excitement of discovery, though discovery is here. Not the alarm of the dramatic, though drama is here too. But the slow, settling awareness of scale. The gradual, patient absorption of the fact that the universe is unimaginably large and complex and three-dimensional. That the pictures we carry of it are simplifications and conveniences, and that the reality behind those pictures is stranger and more beautiful and more interesting than any convenient picture can show. The vertical dimension of the solar system is a small piece of this larger story, but it is a piece that resonates particularly strongly, I think, because it touches on something very personal: our relationship to up and down, our sense of where we are in the universe, our deeply human need to have a floor and a ceiling. There is no floor, there is no ceiling, there is only space, in all directions, and the occasional cluster of matter that we call home. If these meditations on scale and dimension are giving you something, a new way of sitting with the sky, a quiet recalibration of the familiar, we would love to have you as part of the Sleep on Space community. Subscribe, ring the bell, and like this video if it moves you. We are grateful for your company in the dark. Perspective is everything. The choice of how to view the solar system determines, almost entirely, what the solar system looks like. The textbook diagram chose to view the solar system from directly above the ecliptic's north pole, a vantage point that was chosen precisely because it makes the solar system look its most organized, its most disk-like, its most amenable to a clear and instructive diagram. From directly above the ecliptic, the planets do trace roughly concentric circles. The near coplanarity of the major planets is plainly visible. The diagram is educational and broadly correct, as a representation of the inner solar system. But what happens to this diagram when we change the viewing angle, tilt the viewpoint by just a few degrees, rotate it slightly from the pole on view, and the planets' orbits begin to show their true elliptical nature? The circles become ellipses of varying eccentricity. Saturn, with a noticeably elliptical orbit, becomes visibly elongated. Tilt the viewpoint further, to the equatorial plane of the solar system, looking at the ecliptic edge on, and the diagram changes dramatically. Now the planets' orbits appear as lines, thin ellipses seen edge on, and the vertical extent of those orbits becomes visible. Mercury's orbit is a thin line cutting through the ecliptic at a shallow angle. Pluto's orbit is much more steeply inclined. It cuts across the edge on ecliptic at a 17-degree angle, rising visibly above the system's flat plane. Continue past the edge on view, tilt the viewpoint still further, past the equatorial plane, and the appearance of the solar system changes again. Now you are seeing it from below the ecliptic's south pole, and the planet positions are mirrored. Each viewing angle reveals a different aspect of the solar system's true three-dimensional structure. None of them is the correct view. Each one is a valid perspective that reveals certain features and hides others, but there is one viewing angle that is particularly revelatory, and it is one that almost no popular astronomy presentation ever uses. The view from the ecliptic plane, looking perpendicular to the solar system's radial direction, not toward or away from the sun, but sideways along the ecliptic plane, so that the ecliptic itself is a horizontal line in the view. From this angle, you can see the vertical structure of the solar system directly. You can see Pluto's orbit curving above and below the ecliptic by several astronomical units. You can see the puffiness of the Kuiper Belt, its vertical extent clearly visible against the narrower, more confined inner planetary region. You can see the much larger vertical excursions of scattered disk objects, and if you could zoom out far enough to see the Oort Cloud, which would be invisible in any realistic depiction at a scale that also shows the planets, you would see the sphere beginning to form at the outer boundary, the transition from thick disk to thin disk to sphere playing out from the center outward. This edge-on view is the most honest view of the solar system that can be presented in a two-dimensional format, because it is the view that most clearly shows the dimension that the textbook diagram suppresses. When astronomers actually search for new objects in the outer solar system, they do not search only along the ecliptic plane. They search across a range of ecliptic latitudes, a range of heights above and below the ecliptic, because experience has taught them that interesting objects can be found at surprising inclinations. The sky surveys that have discovered most of the known Kuiper Belt objects and scattered disk objects have covered ranges of ecliptic latitude spanning 20, 30, sometimes 40 degrees above and below the ecliptic. Even so, surveys preferentially find low inclination objects because they spend more time near the ecliptic, where the surveys are densest. The high inclination population of the outer solar system is almost certainly undersampled. We know of fewer high inclination objects not because they are rarer, but because they are harder to find. This systematic undersampling of high inclination orbits is one of the ways in which the bias toward the flat persists even in modern astronomical practice. We know the bias exists. We correct for it statistically when we estimate the true population of the outer solar system, but the correction is imperfect, and there is likely a whole population of tilted, highly inclined outer solar system objects that we have not yet detected. Objects whose orbits carry them to high ecliptic latitudes where our surveys are sparse or absent. The vertical solar system is, in part, still unexplored. There may be dwarf planets out there, objects the size of Pluto or larger, orbiting at inclinations of 60, 70 or even 80 degrees to the ecliptic, spending most of their time far from the ecliptic plane where our surveys rarely point. Their orbits might carry them so far from the Sun in the vertical direction that they are effectively invisible to current telescopes. They would be cold, dark, distant and inclined, objects in the vertical frontier waiting to be discovered by some future survey that commits to scanning the full sphere of the sky rather than just the thin band near the ecliptic. The search for Planet 9, the hypothetical large planet whose gravitational influence is invoked to explain the orbital clustering of several extreme trans-Neptunian objects, is partly a search in the vertical direction. Some proposed orbital configurations for Planet 9 have it at relatively low inclination, but others have it at inclinations of 15 to 30 degrees or more. If Planet 9 exists and has a highly inclined orbit, it would spend much of its time far from the ecliptic, potentially in a region of sky that has received relatively little observational attention. The full three-dimensional solar system remains, in significant part, unmapped. The flat diagram is not just conceptually incomplete, it is observationally incomplete. We have preferentially explored the flat part of the solar system because that is where the bright, nearby, easily observable objects live. The vertical part, the high-inclination outer solar system, the Oort Cloud, the scattered disk, remains largely terra incognita, the dark waters off the edge of the known map. There is something both exciting and humbling about this situation. The fact that significant parts of the solar system remain unmapped in the vertical direction means that future discoveries are not just possible but highly likely. The coming decades will see major sky surveys, LESS/Rubin Observatory being the most prominent example, that will scan the sky far more thoroughly than anything before, covering wider ranges of ecliptic latitude, reaching fainter objects, and dramatically expanding our census of the outer solar system in all directions. What we will find, almost certainly, is a population of outer solar system objects, much richer and more three-dimensionally distributed than what we currently know. We will discover highly inclined dwarf planets, highly inclined scattered disk objects, highly inclined Kuiper Belt objects in orbital configurations that challenge current models of solar system formation and evolution. We will find the vertical solar system, in much greater detail and completeness than we have it today. And each discovery will add a point to the three-dimensional map that is replacing the flat diagram in the minds of those who study the solar system professionally. Each inclined orbit will be a new story, a new record of the dynamical history of the outer solar system, a new data point for refining our models of planetary migration and Oort cloud formation and galactic tide effects. The flat diagram is being replaced, slowly but inevitably, by a three-dimensional understanding. Not in popular science, not yet. The textbooks and documentaries and school posters still mostly show the flat solar system because it is simpler and more immediately comprehensible. But in research astronomy, the three-dimensional solar system is already the working reality. The flat diagram is a tool for beginners, a convenient starting point, a necessary simplification, and beginners at some point grow, which is what tonight has been about. We are 90 minutes into our journey beyond the ecliptic, and the map is almost fully dissolved. In the final 30 minutes, we will complete the dissolution, following the thread of unlearning to its most philosophical and beautiful terminus. If this kind of deep, patient exploration of the solar system's hidden dimensions is something you value, please subscribe to Sleep on Space. It means everything to us, and it means more of these journeys for everyone. Every body in the solar system tilts. This is perhaps the single most important sentence in this entire film, and it is the sentence that the flat diagram most completely obscures. Not just orbital inclinations, though those are tilted too, but rotational tilts, the axial tilts of the planets themselves, the angle between each planet's rotational axis and the perpendicular to its orbital plane. Earth, famously, is tilted at 23.4 degrees, the tilt that gives us our seasons, that makes summer and winter possible, that has shaped the evolution of life on this planet as profoundly as any other single physical fact about our world. When the northern hemisphere tilts toward the sun, it is summer in the north and winter in the south. When it tilts away, the reverse. This is grade school astronomy, but the fact that it is grade school astronomy should not lessen our wonder at it. The seasons, the most intimate rhythm of the Earth's year, the cycle that has regulated agriculture and migration and culture for all of human history, exist because Earth's rotational axis is tilted 23.4 degrees from perpendicular to the ecliptic. Mercury's rotational tilt is almost exactly zero, about 0.03 degrees. Mercury spins nearly perfectly upright relative to its orbital plane, which means Mercury has no seasons in the conventional sense. One hemisphere bakes continuously, the other freezes continuously. The only thermal variation comes from the eccentric orbit and the planet's slow rotation relative to its revolution, which creates the bizarre situation of the hot poles, regions near Mercury's equator that receive the most intense solar heating during the planet's closest approach to the Sun. Venus, by contrast, is tilted 177 degrees, which is to say Venus is essentially spinning upside down relative to Earth's reference frame. This extreme axial tilt means that Venus rotates retrograde, opposite to the direction of most solar system rotation, and that the Sun, as seen from Venus, rises in the west and sets in the east. The origin of Venus's retrograde rotation and extreme axial tilt remains one of the unsolved mysteries of solar system science. Was it the result of a massive impact in the distant past, or of complex spin-orbit coupling resonances, or some other mechanism? The debate continues. Uranus takes the prize for extreme axial tilt among the major planets. Uranus is tipped on its side, with an axial tilt of 97.77 degrees, more than a right angle from the perpendicular to its orbital plane. Uranus essentially rolls around the Sun on its side, its poles alternately pointed toward and away from the Sun as it makes its 84-year orbit. During Uranian summer in the North Pole points almost directly toward the Sun, bathing the northern hemisphere in constant daylight for decades, while the southern hemisphere experiences a decades-long polar night. Then, halfway around the orbit, the situation reverses. Uranus's extreme tilt is thought to be the result of a massive collision with an Earth-sized object early in solar system history, an impact so violent that it literally knocked the planet sideways. Saturn's rings, those incomparable structures that have inspired wonder in every human being who has ever turned a telescope toward them, are themselves a tilted feature. Tilted not just in the sense that Saturn's axis is tilted at 26.7 degrees, giving Saturn seasons broadly similar to Earth's, but tilted in the sense that the ring system defines its own equatorial plane, perpendicular to Saturn's rotation axis, and this plane makes a 26.7-degree angle with Saturn's orbital plane. When Saturn is at different points in its orbit, we see the rings from different angles, sometimes nearly edge-on, when they nearly disappear, and sometimes face-on, when their full glory is visible. The tilts of the planets are, like their orbital inclinations, records of the solar system's history, frozen-in signatures of the violence and chance of the early solar system. Every major impact, every gravitational interaction, every spin-orbit resonance has left its mark in the axial tilt of the body that experienced it. Earth's 23.4 degrees may be the result of the giant impact that formed the Moon. The collision with the Mars-sized body called Theia that is thought to have occurred approximately 4.5 billion years ago, early in the solar system's history. Uranus's 97.77 degrees is almost certainly the result of a massive collision. Venus's 177 degrees is a mystery that may involve either a large impact or a complex spin-orbit coupling driven by solar tidal forces over billions of years. Every tilt tells a story of something that happened: a collision, a resonance, a gravitational encounter, a long, slow spin-down driven by tidal forces. The solar system is covered in the fingerprints of its history, and those fingerprints are angles. There is something poignant about this. The tilts of the planets are accidents, or rather, the consequences of specific events that could have gone differently. Earth might have been struck at a different angle, giving it a different axial tilt, giving it different seasons or no seasons at all. Uranus might have escaped the giant impact that knocked it sideways. The solar system might have arranged itself differently, with a different distribution of tilts, a different set of seasonal rhythms, a different history of impacts and near misses. The fact that Earth has a 23.4-degree axial tilt, the fact that we have the seasons we do, that the temperate zones are where they are, that the polar regions experience the extremes of darkness and light that they do, is contingent on a specific impact that occurred 4.5 billion years ago and left Earth tilted at this particular angle rather than some other. Had Theia struck at a different velocity, a different angle, a different impact parameter, Earth's tilt might be 5 degrees or 45 degrees. The biology of Earth, the evolution of its ecosystems, the development of its civilizations would all be different. The angle of our planet's tilt is one of the most consequential accidents in the history of life, and it is an accident that the flat diagram cannot show, because the flat diagram looks at the solar system from above the ecliptic, from a direction perpendicular to the orbital planes, and from that angle, axial tilts are invisible. The flat diagram that gave us our first picture of the solar system is also, in precisely this way, the picture that hid from us one of the most fundamental facts about our home planet. The tilt is invisible in the flat picture. The tilt is real, and there is one more tilt that deserves mention here, because it is the tilt that most directly affects our immediate experience of the night sky, and yet is perhaps the least well-known of all. The tilt of the solar system's invariable plane relative to the ecliptic. The invariable plane is the true mean plane of the solar system, not the ecliptic, which is just Earth's orbital plane, but the plane perpendicular to the solar system's total angular momentum vector. Since angular momentum is a conserved quantity, the invariable plane is, in a precise physical sense, the most stable reference plane in the solar system. It does not change over time, except on extremely long timescales due to galactic tidal effects, while the ecliptic shifts slightly as Earth's orbit is perturbed by the other planets. The invariable plane is tilted approximately 1.57 degrees relative to the ecliptic. This is a small angle, but it means that when we use the ecliptic as our reference plane and measure inclinations relative to it, we are measuring inclinations relative to a plane that is itself slightly tilted relative to the physical reference plane of the solar system. Our conventional reference has a built-in tilt relative to the physical reality. This is a beautiful small irony. The reference plane we use to measure tilts is itself slightly tilted. The zero line is not quite zero. The floor has a barely perceptible slant that we have chosen to ignore for the sake of convenience. In a universe full of tilts, even the reference is tilted. We have been speaking about the vertical dimension of the solar system primarily in terms of orbital mechanics, inclinations, eccentricities, tilts, but there is another kind of vertical that physics has revealed in recent decades, one that operates at a completely different scale and speaks to a completely different aspect of the three-dimensional universe. In 2015, the LIGO detector, the the Laser Interferometer Gravitational Wave Observatory detected gravitational waves for the first time in human history. These waves were produced by the merger of two black holes approximately 1.3 billion light-years from Earth, and they arrived at Earth as a tiny, brief distortion in the fabric of space-time. A compression and stretching of the distance between the LIGO detector's mirrors by an amount smaller than a proton's diameter. Gravitational waves travel through space-time in all directions, not confined to any plane. They are produced by massive accelerating objects, merging black holes, colliding neutron stars, core collapse supernovae, and they radiate outward in all three dimensions, spherically symmetric to first approximation, though with a characteristic quadrupole pattern that means the waves are strongest perpendicular to the orbital plane of the merging objects, and weaker in the plane itself. The detection of gravitational waves is relevant to our story for several reasons. First, gravitational waves are a literal embodiment of the vertical dimension. The waves from a merging binary system, two objects orbiting each other in a plane, are strongest in the direction perpendicular to the orbital plane, in the vertical direction. If you were in the orbital plane, you would detect weaker gravitational waves than if you were above or below the orbit. Gravitational wave astronomy is, in a precise sense, listening to the vertical dimension, collecting signals that are strongest in the direction perpendicular to the plane of motion. Second, the detection of gravitational waves has opened an entirely new observational window on the universe, one that transcends the limitations of electromagnetic astronomy, which is forever confined to the light-emitting surfaces of objects. Gravitational waves pass through all matter without absorption. They carry information from the deepest interiors of massive objects, from events that are electromagnetically invisible. They come from all directions, from every point on the celestial sphere, not preferentially from the galactic plane or the ecliptic plane. Gravitational wave astronomy is three-dimensional astronomy in a deep sense. The universe as seen through gravitational wave detectors is a universe without a preferred plane. Sources are distributed across the full sphere of the sky, at all distances, at all orientations. There is no ecliptic in gravitational wave astronomy. There is only the sphere. The detection of gravitational waves is also relevant, because it has given us a new tool for measuring the three-dimensional structure of the universe, including, potentially, the three-dimensional structure of our own galaxy and the objects within it. Within our galaxy, there are many potential sources of gravitational waves, merging stellar mass black holes and neutron stars in binary systems, the periodic gravitational waves from rapidly rotating neutron stars, the background hum of unresolved binaries. These sources are distributed throughout the galaxy's three-dimensional volume, not confined to the thin disk of the galactic plane. When future gravitational wave detectors, particularly LISA, the Laser Interferometer Space Antenna planned as an ESA mission, map these sources, they will be creating a three-dimensional map of the galaxy that transcends the limitations of optical astronomy. Optical astronomy can see the galaxy's stars and gas clouds, but it is limited by dust absorption, which is concentrated in the galactic plane and obscures much of the galaxy from optical view. Gravitational waves pass through dust freely. A gravitational wave survey of the galaxy would be unobscured. It would see sources at all galactic latitudes, at all heights above and below the galactic plane, with equal sensitivity. It would be a genuinely three-dimensional census of compact objects in the galaxy. This is one of the ways in which 21st century astronomy is in the process of completing the shift from two-dimensional to three-dimensional that has been underway since Copernicus took the Earth out of the center of the universe. We began, as a species, with a two-dimensional astronomy, a flat sky, a dome of fixed stars, a system whose structure we perceived as projected onto the celestial sphere. We slowly added the third dimension, parallax measurements, proper motion studies, radial velocity surveys, building up our picture of the three-dimensional distribution of stars and galaxies. And now, with gravitational wave astronomy, we are opening a new window that is inherently three-dimensional and inherently non-planar, that perceives the universe as the sphere it is rather than the map we projected onto it. The flat picture is being replaced, not by a picture, but by a sphere, not by a diagram, but by a direction, in all directions, simultaneously. We are living, I think, in a particularly fortunate moment in the history of humanity's relationship with the cosmos. We are the first generations to have access to truly three-dimensional maps of the universe at multiple scales, to have parallax measurements of billions of stars from the Gaia satellite, to have gravitational wave detections from hundreds of compact object mergers, to have detailed three-dimensional models of the outer solar system, to have simulation results that track the solar system's dynamical history over billions of years. We are the first humans who can, in principle, know the three-dimensional solar system rather than the flat one. We have access to the numbers, the inclinations, the eccentricities, the orbital architectures, the distances, that allow us to build the true picture in our minds, however imperfectly. We can, if we choose, unlearn the flat diagram and replace it with something closer to the truth. This is a privilege that did not exist a generation ago, and it is one that most people who possess it have not fully exercised. The flat diagram persists, in textbooks, in popular science, in the casual imagination of anyone who glances at a solar system poster. It persists because it is simpler, because it is more immediately comprehensible, because the effort of truly absorbing a three-dimensional solar system is greater than the effort of glancing at a flat one. But the effort is worth it, because what you get, on the other side of that effort, is something more beautiful than the flat picture. You get the real solar system, not the simplified map, but the actual thing. Not the textbook diagram, but the 4.5 billion-year-old object, tilted and inclined and wobbly, embedded in a galaxy that is itself tilted, and embedded in a supercluster that is itself embedded in the cosmic web. Every layer of structure tilted at some angle to every other layer, nothing flat all the way down, directions dissolving into each other as you scale up until you arrive at the CMB and find that the universe itself has no preferred orientation, but was always, everywhere, equally in all directions at once. 100 minutes of quiet exploration, and we are approaching the end, the final dissolution. If this journey has changed how you think about the sky above your head, please subscribe to Sleep on Space and leave a like. We are a small community of people who find meaning in the deep spaces between things, and we are grateful for every single one of you. We have been on a journey of dissolution. We began with a flat picture, the beloved, familiar, laminated solar system diagram, and we have been systematically dissolving its flatness, peeling back its convenient simplifications, revealing layer by layer the three-dimensional reality behind the two-dimensional representation. We dissolved the inner planet's perfect coplanarity, showing Mercury's 7 degrees, the wobbles and tilts of every planet, the inclined orbits that make the inner solar system three-dimensional. We dissolved the asteroid belt's flatness, finding Pallas at 34.8 degrees, finding the full range of inclinations that makes the belt a three-dimensional structure, rather than a thin ring. We dissolved the Kuiper Belt's disk, showing the hot population with high inclinations, the scattered disk with Eris at 44 degrees, the progressive puffing of the outer solar system as you move away from the sun. We dissolved the planetary solar system entirely, revealing the Oort Cloud as a sphere 1.6 light-years wide that makes the entire ecliptic plane look like a thin kernel at its center. We dissolved the solar system's galactic context, showing its 60-degree tilt relative to the Milky Way, its carousel bobbing through the galactic plane over 6470 million-year cycles, its intimate connection to the three-dimensional structure of the galaxy. We dissolved the concept of preferred directions, showing that up and down are local constructs, that every reference plane is defined by the angular momentum of the structure it describes, that there is no cosmic flaw. And now we arrive at the final dissolution. The cosmic microwave background is 13.8 billion years old. It was emitted when the universe was approximately 380,000 years old, a baby by cosmic standards, though 380,000 years is older than the entire existence of our species. It has been traveling ever since, cooling and redshifting as the universe expanded, arriving at us now from every direction with almost exactly the same temperature. The CMB is the oldest light. It is the farthest limit of our direct observation. We cannot see farther back than the surface of last scattering from which the CMB was emitted, because before that moment, the universe was opaque, a hot, dense plasma in which photons were continuously scattered by free electrons. The CMB is the wall at the edge of the observable universe, the surface from which the universe first became transparent to its own light. When we look at the CMB, we are looking at the universe as it was before there were stars, before there were galaxies, before there were planets, or comets, or solar systems, or anyone to look at any of it. We are looking at the raw material of everything, the slightly denser regions that would eventually, over billions of years, contract under gravity into the first stars, the first galaxies, the first supernovae that scattered the heavy elements needed for planets, the first planetary systems, the first planets that developed chemistry, and eventually, in one particular galaxy, around one particular star, on one particular planet, the first beings to turn their eyes upward and ask, what is all this? The CMB has no ecliptic. It has no galactic plane. It has no preferred orientation. It fills the sky with equal intensity in all directions, a sphere of ancient light that predates every structure, every plane, every angular momentum vector, every orbital inclination in the universe. If you could remove the solar system, the galaxy, the local group, the supercluster, if you could exist in a universe that contained nothing but the CMB, there would be no up, no down, no ecliptic, no floor, no ceiling, just light, in all directions equally. The CMB is the ultimate dissolution of the flat picture. It is the proof, written in the oldest light in existence, that the universe does not prefer any particular direction. The ecliptic is a local human invention. The galactic plane is a parochial astronomical convention. The invariable plane is a useful engineering reference. All the planes, all the reference frames, all the ups and downs and aboves and belows, they all exist only locally, only within the context of specific rotating objects, specific angular momenta, specific histories of specific collapsing clouds of gas. Strip away the structure, and you get isotropy. Strip away the local, and you get universal. Strip away the map, and you get the territory. Let us take one final step. In the far future, if physics is right about the universe's long-term evolution, the structures we have been discussing will dissolve. The solar system, billions of years from now, will be disrupted when the sun expands into a red giant and engulfs the inner planets. The outer planets may survive, in some form, orbiting a dim white dwarf. The Oort Cloud will be partially stripped by the red giant phase, sending billions of comets into new trajectories. The Milky Way and Andromeda will merge, approximately 4.5 billion years from now, disrupting the galactic plane that we have been discussing, scrambling the orbital planes of billions of stars, creating a new larger elliptical galaxy from the merger of the two spirals on even longer timescales. Trillions of years. The stars will exhaust their fuel and die, one by one. The last red dwarfs will burn out in approximately 100 trillion years. After that, the universe will enter what cosmologists call the degenerate era, a universe of white dwarfs, neutron stars and black holes, slowly cooling toward equilibrium. Protons may eventually decay, reducing all ordinary matter to energy. Black holes will evaporate through Hawking radiation over timescales of 10 to the 82nd power years. Eventually, the universe may reach a state of maximum entropy, the heat death, in which all gradients have been eliminated, all temperature differences resolved, all structure dissolved. In this final state, there will be no ecliptic, no galactic plane, no up or down, no near or far, no fast or slow, no hot or cold, nothing but the even distribution of energy across the unimaginably expanded volume of space. A universe in its most isotropic possible state, as close to the homogeneity of the CMB as it is possible to get. But cold, cold beyond any temperature we have words for, cold in every direction equally. In the heat death of the universe, the question which way is up is finally, definitively, permanently answered. There is no up. There never was. But we are not in the heat death of the universe. We are here, now, in the middle of an extraordinary cosmological moment. A universe that is 13.8 billion years old, still full of structure, still full of galaxies and stars and planets and complex chemistry, still warm enough in some places for liquid water, still providing the specific conditions under which minds can exist and ask questions about the universe they find themselves in. We are sitting on a small rock that orbits a medium star at an inclination of 23.4 degrees to its equatorial plane, in an orbital plane inclined 60 degrees to the galactic plane, in a galaxy that bobs above and below its own midplane every 64 to 70 million years, in a universe whose deep structure was set 13.8 billion years ago by quantum fluctuations that cared nothing for any particular direction. We are tilted. We were always tilted. The flat picture was never true. But it was necessary. Necessary as a first approximation, as a beginning, as the foundation for the more accurate picture that could only be built once the first one was understood, and then gently, carefully, respectfully taken apart. The flat diagram that a teacher placed before you in a classroom all those years ago was a gift. It was the beginning of a journey that, if you follow it, leads here, to this film, to these numbers, to these scales, to this final dissolution of up and down into the ancient, equal, isotropic light of the early universe. Every simplification is an invitation to a more complex truth. Every map is an invitation to the territory. The textbook diagram invited you, without knowing it, to this. Look at this. Really look at it. This is the solar system. Not the simplified one, not the flat one, not the convenient one. The real one, with Mercury's 7-degree tilt, and Pluto's 17-degree inclination, and Eris's 44-degree orbital plane, and Pallas cutting across the ecliptic at 34.8 degrees, and the Kuiper Belt thickening as you move outward, and the Oort Cloud wrapping the whole thing in a sphere 1.6 light-years across. And all of it, the flat part, the puffy part, the spherical part, tilted 60 degrees relative to the plane of the Milky Way, and bobbing up and down through that galactic plane in a 64-million-year cycle that may, in ways we are still investigating, be connected to the rhythms of mass extinction on the surface of our pale blue world. This is the solar system, and the flat diagram you were given as a child was a door. A door that opened onto this. You can look at the night sky differently now, when you look up and see the planets arranged in their familiar path across the sky. The ecliptic, the zodiac. You can know that you are seeing only a thin slice of the solar system's true structure, a cross-section through a three-dimensional object that extends far above and far below the plane of your sight. The planets visible to the naked eye are in the flat part, the central disk, the kernel. Above and below that disk, invisible to you but real and present, are the inclined orbits of Pluto and Eris and hundreds of thousands of Kuiper Belt objects. Farther out, surrounding the visible solar system in a sphere of frozen silence, the Oort Cloud waits. Billions of bodies in orbits at all inclinations, tilted above and below the ecliptic plane at every possible angle, occasionally jostled by a passing star or the gentle gradient of the galactic tide and sent falling inward toward the sun, on journeys that take centuries or millennia. When you see a comet in the night sky, when you see that smear of luminous gas trailing across the dark, you are seeing a visitor from the vertical, a body that came not from the flat disk of the planets, but from the spherical shell of the Oort Cloud, descending from above or below the ecliptic on a steep inclined orbit, briefly visible in the inner solar system before swinging around the sun and heading back out to the cold and the dark. You are seeing the third dimension of the solar system, briefly lit. And when you look up at the Milky Way, when you find a dark sky and let your eyes adjust until the galaxy's light becomes visible as that ancient, luminous band arching overhead, you can know that you are looking at it from the inside, at an angle. The solar system's ecliptic plane is inclined 60 degrees to the galactic plane, and you are embedded in that inclined ecliptic plane, looking across at the galaxy's disk at an oblique angle. The Milky Way's light comes from a direction that is 60 degrees away from the direction that is above the solar system. There is no universal up, but there is the direction perpendicular to the ecliptic, the direction the Earth's north pole points, which is also the direction from which the solar system was traditionally viewed in the textbook diagram. And that direction, that local up, is pointed 60 degrees away from the galaxy's north pole, 60 degrees away from the direction perpendicular to the galactic disk, at some angle to the direction of the local galactic magnetic field, at some other angle to the direction of the cosmic microwave background's dipole moment. Every up is inclined to every other up. We are a tilted species on a tilted planet in a tilted solar system in a tilted galaxy, looking out at a universe that has no tilt, because it has no preferred direction, a universe that is the same everywhere and in every direction in its most fundamental nature, a universe that generated all this beautiful, inclined, three-dimensional structure from an initial state that was perfectly, exquisitely isotropic. We are the angles in a universe that has no angles. We are the planes in a universe that has no planes. We are the maps in a universe that is not a map. And yet, even in the pure black, even in the silence of cosmological scales and geological timescales, and the eventual heat death that awaits all structure in this universe, even in the dissolution of every up and every down, you are here, looking up, wondering, the capacity to look at a flat diagram in a childhood classroom, and eventually, Through curiosity and time and the accumulated work of thousands of scientists across many centuries, arrive here at this edge of understanding. That wondering is itself one of the most extraordinary things in the observable universe, not because it is cosmologically significant. In any objective physical accounting, the mental activity of a few billion beings on a small planet in the outer arm of a spiral galaxy is negligibly small compared to the total mass energy content of the observable universe. But because it is what we know, from the inside, we are the universe's way of asking itself which way is up. And the answer? The honest, careful, deeply earned answer is always every way. No way. The question dissolves in the light. The light is ancient. The question remains, if this journey, from the flat textbook diagram to the edge of cosmological isotropy, has been worth 2 hours of your night, we would be deeply honored by your subscription to Sleep on Space. Leave a like, share this with someone who looks up at the night sky and wonders, and join our community of quiet explorers. We make these films with care and gratitude, for people who are not afraid to let the darkness be as large as it actually is. Thank you for traveling with us. We will see you in the dark. There is a letter from Voyager 1. Not a letter it can write, of course. It is a spacecraft, a machine, a construction of aluminum and plutonium and transistors launched in the autumn of 1977 from Cape Canaveral, Florida. But its trajectory is a kind of letter, the path it has taken through the solar system and now beyond it, out past the heliopause, into the interstellar medium, at an angle of approximately 35 degrees north of the ecliptic plane. That path is a record, written in velocity and direction, of every gravitational interaction it has experienced. The trajectory of Voyager 1 is a message from the three-dimensional solar system, transmitted in the language of orbital mechanics. And somewhere in the outer solar system, in the Kuiper Belt, or the scattered disk, or the distant reaches of the Oort Cloud, there are billions of bodies that have never been observed, that may never be observed, that trace their inclined orbits in the dark without any witness. Their paths, too, are records. Their inclinations are histories. Their trajectories are letters written in the language of gravitational dynamics, addressed to anyone patient enough to read them. The solar system is full of these letters. They are written in angles, in tilts, in the deviation of orbits from the flat. We have been learning to read them. We have been learning that the flat picture was the first sentence of a much longer letter, and that the letter, when read in full, describes not a flat disk circling a yellow star, but a three-dimensional, dynamically complex, historically rich, gravitationally interconnected structure of extraordinary variety and beauty, tilted 60 degrees to the galaxy it inhabits, bobbing gently through the galactic plane in a cycle longer than the age of the dinosaurs, embedded in a universe that is, at its deepest level, equally beautiful in all directions. The letter, read in full, is love. The letter, read in full, is wonder. The letter, read in full, says, "This is what exists. This is the real shape of things. This is the vertical, the inclined, the three-dimensional truth of the place you call home. Put down the flat diagram, pick up the sphere, and look. In all directions equally,